Hello friends, welcome back to the video lecture series on control system. Today we will start with signal flow graphs. So this lecture is continuation of lecture 7. So we will start with Mason's rule. The block diagram reduction technique requires successive application of fundamental relationships in order to arrive at the system transfer functions. On the other hand, Mason's rule for reducing a signal flow graph to a single transfer function requires the application of one formula. So here in block diagram reduction techniques, successive application of fundamental relationship means step by step we have to do some simplification in block diagram using reduction techniques. But other hand, in Mason's gain formula or Mason's rule, we required only one formula, means whatever be the signal flow graph is there, from that we can easily get directly the transfer function value. The formula was derived by S.J. Mason when he related the signal flow graph to the simultaneous equations that can be written from the graph. So this is the Mason's rule formula, or we can say Mason's gain formula. The transfer function C of S upon R of S of system represented by a signal flow graph is nothing but summation I varies from 1 to n pi del I whole upon delta. So here what are different terms in this formula we must know. So n is number of forward paths. As we studied in the last lecture, what is the forward path? So we can easily calculate number of forward paths. Then pi. So pi is the ith forward path gain. So it is nothing but forward path gain for that particular uh, ith forward path. Then delta is determinant of system, and delta I is determinant of ith forward path. So here delta is called signal flow graph determinant or characteristic function, since delta equal to 0 is the system characteristic function. So we can easily say delta is nothing but characteristic function. So it is bit difficult to understand from this formula what is delta, what is pi, what is delta I. So we will go in great detail with algebraic equation what is the delta mathematically. So delta is nothing but 1 minus sum of all the individual gains plus sum of the products of the gains of all possible two non-touching loops minus sum of the products of the gains of all possible three non-touching loops. Likewise, this plus minus way, as many combinations possible we have to consider. Same way, delta I is nothing but value of delta for the part of the block diagram that does not touch the ith forward path. So if there are no touching loops to the ith forward path, then delta I is equal to 1. So once again, if there is a confusion while understanding what is delta and delta I, we will refer few examples, and after understanding all those examples, I am sure you are bit comfortable with finding delta and delta I. In case you get any doubt regarding Mason's gain formula, please mail me on my email ID. So systematic approach first we will understand, and then we will apply this approach on various examples. So first step is calculate forward path gains pi for each forward path. Then calculate all the loop transfer functions. Consider non-touching loops 2 at a time. Same way non-touching loops 3 at a time, etc. Means if there are 4 non-touching loops, then we have to consider all those things. In this manner, calculate delta from step 2, 3, 4 and 5, and calculate delta I as portion of delta not touching forward path I. So let's see one example. So here example is apply Mason's rule to calculate transfer function of system represented by this signal flow graph. So here first step is forward path gains. So there are two forward paths. First is G1, G4, G2 in this manner straight line, and second is G1, G4, G3. So this is one forward path and this is another forward path. So there are two forward paths, means I value is varies from 1 to 2. So P1 delta 1 plus P2 delta 2 upon delta is our final formula of Mason's gain for finding transfer function. Then we have to find feedback loops. So how many feedback loops are there? First is G1, G2, H1. So this is L1 loop. Second is G1, G2, G4, and this is H2. So minus sign is there. So minus G1, G2, G4, H2. And third is G minus G1, G3, G4, H2. So this is first loop L1, this is second loop L2, and this is third loop L3. So there are no non-touching loops. All loops are connected with each other. There must be single node is common in each and every loop. So there are no non-touching loops. So delta is nothing but 1 minus sum of individual loop gains only. So 1 minus in bracket L1 plus L2 plus L3. So this is what we delta calculated. Then our next stuff is P1 delta 1 plus P2 delta 2 we have to find. So here delta 1 is 1 because there is all the loops are touching to the forward path 1. Same way for forward path 2, all the loops are touching. So delta 1 and delta 2 is equal to 1. P1, P2 we know. By substituting all these value P1 delta 1 plus P2 delta 2 upon delta, we get simplified transfer function value directly. So no need to do rigorous simplification in the block diagram or signal flow graph. We get directly the answer. Same way second example. So here forward paths are, so this is red line shows one forward path and blue line shows another forward path. So G1, G2, G3, G4, this is a forward path 1 gain and this is a second path gain. Then number of loops. So L1, L2, L3 and L4, these are the four loops. Non-touching loops, of course, L1 with L3, L4, L2 with L3, L4. So these are four non-touching loops. Now three non-touching loops are absent. So delta is nothing but 1 minus summation of individual loop gains plus summation of two non-touching loop gains, product of two non-touching loop gains. So by substituting all these values, we get this is nothing but our delta. Next we have to find delta 1 and delta 2. So for delta 1, so for this path non-touching loops are L3 and L4. So delta 1 is 1 minus L3 plus L4. There are two non-touching loops are absent. So similar way we can find delta 2. For delta 2 forward path 2, L1 and L2 are non-touching. So 1 minus summation of L1 and L2 is the delta 2. So in this manner we just find delta 1 and delta 2. P1 and P2 we know. Now we have to just substitute all these value in P1 delta 1 plus P2 delta 2 upon delta. We get this is the huge answer. But great thing about this method is we get directly the answer. Just finding P1 delta 1, P2 delta 2 and delta and substituting all those values we get directly answer. So this is a faster method than block reduction technique. One more sum. So here first we need to find forward path gains. So this is one forward path. So next is we have to find the loops. So this is first, second, then this is third loop and fourth loop. So this is third and this is fourth. So non-touching L1, L2, these are non-touching. Then L1, L3 is non-touching. L2, L3 is non-touching. So there are three combinations of non-touching loops. Also L1, L2 and L3, three non-touching loops also present. So here delta 1 is nothing but, so for this non-touching loop is this L3 G7 H4. So 1 minus G7 H4 is nothing but delta 1. Delta we can easily calculate, 1 minus individual loops plus two non-touching product of two non-touching individual loops minus three non-touching individual loops, product of three non-touching individual loops. So now we know delta 1, we know P1, we know delta. So just substituting all these value we can get our transfer function answer. Now next step is, this is a different kind of sum. So here block diagram is given and we need to draw signal flow graph of given block diagram. So here what we will do, this summing point or takeoff point we will consider as node. So this is our RS, then ES, then this is X1 of S, then X2 of S, then X3 of S and C of S. So here between RS and ES nothing is there, so 1. Then C of S feedback to the E of S, so this is minus H3 because negative feedback is there. Then between E of S and X1 of S, G1 is there, X3 get feedback to X1 with minus H2 negative feedback. Then G2 connected between X1 and X2 and X2 from C of S minus H1 is feedback. Then between X2 and X3 G3 is connected, and between X3 and CS G4. So this is simple flow signal flow graph we can draw, and from this signal flow graph diagram we can easily find transfer function as we studied earlier. Now next example. So this is different kind of example in which electrical system or network is given and we have to find signal flow graph for this electrical circuit, and from that we can easily find transfer function. So first step, we just apply KVL. So we get V1 of S is equal to, this is across capacitor whatever be the voltage, plus voltage across resistance, and V2 is nothing but voltage across resistance. So here we can easily write I1 of S is nothing but so C of S is get multiplied, and I1 of SR, so I1 of SR is nothing but V2. So we can easily write I1 of S from these two equation is nothing but CS V1 of S minus CS V2 of S. So this is one equation. Now there are three variables V1, V2 and I1. So we put three nodes because as many variables as many nodes. So between all this relation we have to draw over here. So I1 is nothing but C into S V1 of S. So here CS is multiplication, then minus CS from V2 to I1, yes, minus CS. Now V2 of S is I1 of S R, so here R is coming. So I1 and V2, all this relation is perfectly alright. So this is our signal flow graph diagram. So from that signal flow graph diagram we can easily plot or get the transfer function of system. So this is now second example where mechanical system is given. So here there are two masses M1 and M2 and force is applied on M1. So we can easily write our equation. F is nothing but force due to the mass and the spring. So due to the mass M1 S square x1, and due to the spring K1 x1 minus x2. Whereas in on second body mass M2, force is not directly applied, so 0 is equal to due to the mass M2 S square x2 plus K1 is in between M2 and M1, so K1 into x2 minus x1 plus K2 x2. So these are two equations. From that we get F plus K1 x2 is equal to, here we are x1 get common, so we get m1 s square plus f1s plus k in bracket, and similar way k1 x1 is equal to, if x2 is common from second equation we get this equation. So just substitute this first bracket m1 s square plus f1 of s plus k1 as a capital A, and m2 s square plus f2s plus k1 plus k2 as a capital B. From that, substituting as a and b, we get simplified equation as a x is equal to 1 by af plus k1 by a into x2, and x2 is nothing but k1 by v into x1. So these are two simple equations, and we can easily plot as a signal flow graph for these two equations. So this is our signal flow graph. So from this we can easily find transfer function. For that, first we need to find forward path, then feedback loops, then delta and delta 1. So here forward path is 1, so simple formula is P1 delta 1 upon delta. So forward path, by substituting all these values we can easily get this is the transfer function for a given mechanical system. So thank you for watching this video. In the next lecture we will start with lecture 9, which is on time domain analysis.